Welcome to Virtual Open Systems website. In this video, Virtual Open Systems is showcasing an application of its Automotive mixed-criticality virtualization software stack product, VOSySmcs. VOSySmcs consists of a full-fledged software stack to support a modern generation of virtual car cockpit where the in-vehicle infotainment system and the instrument digital cluster are consolidated and interact on a single platform. VOSySmcs is based on a key component called VOSySmonitor, a ISO 26262 certified system partitioner, that provides a system-wide security approach to isolate the critical domain from the non-critical applications. In this demonstrator, VOSySmcs is running on the Renesas R-Car H3 Salvatore XS. The critical domain is able to receive CAN messages from an external ECU and reacts according to the event received, such as displays the digital telltales, while the non-critical domain executes the IVI application. Both domains can interact each others by using VOSySmonitor services. VOSySmcs stack is composed by a virtualized environment enabled with Linux KVM where several non-critical applications like the navigation map are executed. In the critical domain, FreeRTOS is running several real-time tasks which are considered safety critical, such as the digital telltales display. In addition, FreeRTOS has been extended with a CAN driver in order to receive information like vehicle speed, diagnostic, turn signal from an external platform. FreeRTOS is able to share some CAN data with Linux through VOSySmonitor service. For example, the 3D instrument cluster, controlled by Linux, is displaying the speed instruction shared by FreeRTOS, that this latter receives from the external ECU through the CAN bus. As you can see, the CAN bus links the Renesas R-Car H3 Salvatore XS to an external ECU, simulated with a Raspberry Pi 3 board in this demonstrator. A touch panel is connected to the Raspberry Pi 3 platform and allows the generation of CAN messages, like speed instruction, that are transmitted to the R-Car H3 Salvatore XS. FreeRTOS, which is extended with a CAN driver, receives this message and shares the speed information with Linux in order to allow the 3D instrument cluster to display the gauges animation, which move until reaching the speed instruction set with the touch panel. With the Safe Split Display feature, VOSySmcs enables the integration of safety-critical and non-critical information on a single display, while providing rendering guarantees for the safety-critical output. As a matter of fact, FreeRTOS has been extended with graphic support in order to display the digital telltales without being impacted by the execution of the non-critical domain. When we generate an event from the touch panel to simulate an engine problem or to control the turn signal, FreeRTOS receives the message sent by the Raspberry Pi 3 on the CAN bus. Then, it displays the corresponding telltales on the cluster screen. Of course, FreeRTOS is still able to share the speed instruction with Linux when it receives the corresponding information on the CAN bus. The Safe Split Display feature is of the utmost importance to provide rendering guarantees of the safety-critical output related to digital telltales, but we will highlight it later in the video during the Linux reboot. A web server virtual machine runs an HVAC panel application on which a user can control the fan speed. The virtual machine forwards, through VOSySmonitor, the command to FreeRTOS that is in charge to control the fan speed. As you can see, the fan is linked to the VOSys extension board on the Renesas R-Car H3 Salvatore XS where FreeRTOS can control its speed. On the other hand, the HVAC panel hosted by the virtual machine is displayed on a screen connected to the Renesas R-Car H3 Salvatore XS. When the user requests to increase the fan speed from the HVAC interface, the order is forwarded from the virtual machine to FreeRTOS through VOSySmonitor. Once the instruction received, FreeRTOS updates the control command and we can see that the fan speeds up. Of course, we observe the same behavior on the other side. The fan rotation decreases if the user wants to reduce the ventilation speed. In VOSySmcs stack, the key component VOSySmonitor is able to detect potential failures in the non-critical application, and can reboot it without impacting the execution of the critical domain. First, let's start some animations on FreeRTOS side with digital telltales and warning. Then, from the touch panel, an event is generated with the red button in order to force a failure on the Linux system. The failure has been correctly detected and a warning message on top of the cluster screen is displayed by FreeRTOS in order to inform the user about this system error. When VOSySmonitor detects the Linux crash, it restarts the non-critical domain without impacting the critical execution of digital telltales from FreeRTOS. Finally, the Linux applications are automatically restarted on the different screens and it is possible to use them like the digital cluster animations. It is important to notice that the critical domain has never been impacted and its tasks are always operational. Thanks for watching the video of VOSySMcs demonstrator. If you need more information, don't hesitate to visit our website with the following links, or you can send a mail to contact@virtualopensystems.com.